so this lesson is 222, and we are looking at universal gates, specifically the NAND gate. So this is the first of the universal gates that we're going to be taking a look at. And in this presentation, we're going to do a lot of stuff. We are going to be looking at the basic function of a NAND gate. We're going to look at how we can actually swap a NAND gate into an AOI circuit and replace AND and OR and inverter gates with the NAND gate. And then we are then going to look at how we re-implement it, so go from AOI into the NAND, NAND into AOI, back and forth. And then we're going to compare the two so we can see how we can actually create a more efficient circuit using NAND gates. So first, let's start by looking at the truth table and the sequence of a NAND gate. So if you look at the diagram, you can see that X and Y are our inputs. When they are going into the AND function of this gate, they are coming together. So the only way we get an output is if we have both of them. So if Y is a 0, X is 1, nothing's happening. This is still an AND gate. So all of the truth table functions of an AND gate still apply. The difference becomes in here, where we have this inverter symbol. So NAND stands for not AND. I know, mind-blowing. So what that means is that when we have X and Y going into this gate, we then end up with Z equaling X naught Y naught, which is also equal to X naught or Y naught, okay? So we do get an equivalent statement here. Now, if we look at the truth table, you can see where we get the outputs. Remember that that circle is a representative of an inverter. So we have X as 0, Y as 0, Z is giving us a 1. That's because of this little bubble right here. Okay, when we have X is 0 and Y is 1, we get an output of 1. Why? A little bubble. Okay, because typically in an AND gate, that would give us a 0. Okay, 1 and 0, obviously we get the 1, and then when we have both of them, nothing. And that's because we have the NOT function in there. So while this works as an AND gate, it's almost like an AND gate mixed with an inverter. So consider it like a remix of the gates. So let's look at the NAND gate if we were to use it as an inverter gate. So again, that's before the bubble that we're looking at. X and X is equal to X prior to the bubble. Okay. Once we have after the bubble, that's when we get that inverter function. Okay, now again, we have the AND gate. We can use this as an AND gate, but it's going to end up in some funky business on the end because of that inverter function. So if you look at the diagram at the top, we have our NAND gate up here. So we end up with X and Y right here, but then it goes through the inverter, and that's when we end up with the X naught naught, Y naught naught. So I know the naught naughts have returned. So if you look down at the truth table, we can see again is 0, 0, 0. We got 0, 1, 0, 1, 0 gives us a 0. So we need all of the functions in order to equal a 1. So in order to get that typical AND gate function, we have to couple it with a NAND gate as an inverter. That's a double sequence there. Okay, now we can get even trickier, and we can use the NAND gate as an OR gate. This is going to require 2 inverters with a NAND gate afterwards. So in order to make the AND or OR functions coupled together in a way that we would do with a traditional AND gate or OR gate, we have to use a sequence of NAND gates, if you're not noticing that trend. So again, if we look down here at the truth table, 0, 0, 0, that would make sense because we have now made it so that this is the OR gate. Now we have it so it's 0 or 1 is giving us a 1 output. 1 or 0 is giving us that 1 output. And then when we have both of those sequences, we are also getting a output of 1. So it takes those 3 in order to create that OR gate function using only NAND gates. So we have an equivalency between AOI and NAND. So if we're taking an AND gate over here and then using NAND only as our logic, this is our setup. If we have an OR gate and we're converting it into a NAND only equivalency, we have to use 3. And then the inverter is a 1-to-1 situation where we just have to double up on the back end here and we can get our inverter. All right. So let's take a look at how we actually would implement NAND into a circuit. So when you start from a logic expression, we have to start by designing the AOI circuit. So we still have to start with the traditional way that we've learned already, by putting in our AND gates and our OR gates, depending on what the expression statement is saying. After you have identified all of the AND and OR gates in the correct locations, we then implement the NAND gate. So we just do a swap. So basically, we would take a diagram like this and we would say, okay, I've got 3 AND gates. I'm going to put in my NAND gates in replacement of that. So you would essentially remove this diagram and put in this anywhere where you had an AND gate. Same thing for OR or inverter. After we had those, we would have to obviously redraw the circuit, and then we would identify and eliminate any double inversions. So that's the back-to-back inverter setup. And then we can create the final circuit. So let's take a look at an example. So we are going to design a NAND logic circuit that's equivalent to this AOI circuit. So you'll see that we have an inverter coming out of C, 2 AND gates, and then a final OR gate. So our second step here is to identify the replacements that we need. So obviously this inverter is going to get swapped right here with this inverter. We have 2 AND gates down here, so they're going to get swapped with the AND components for NAND. So we have the NAND gate followed by the inverter NAND gate. And then we are going to pop in the inverter gates plus the NAND gate. So the NAND inverter with another NAND into the placement of the inverter. And I know right now you're going, hang on, you said this was more efficient than AOI. It can be. That's in this next step. This next step is where we actually redraw the circuit and we start to look for our double inversions. So right now what I have to do is I'm going to, in step 4, look for any double inversions that I have. You can see here, I have 2 of these set up as the inverter. We know that because the tails are tied, and they're followed by another inverter. That means we can pluck out all 4 of those. The end result is then that we only have 4 gates total in this entire circuit. So that's giving us 1 NAND acting as an inverter, 2 NAND gates here, and then the third one as our final NAND gate. Now, we can prove that this is equivalent to the AOI logic that we had by just looking at the outputs that we're getting at each of the gates. And now, let's look at how we can tell that one is more efficient than the other. So if we look over here at the AOI circuit that we had an inverter, 2 AND gates, and an OR gate at the end. If we look at actual circuit implementation, what we're putting into the breadboard, we have the 74LS04, which would be the HC04 in Tinkercad, and we're using 1 gate on there, okay? And there are a total of 6 gates on that IC chip, so we're using 1 IC. Here we need the 08 chip, okay, and then we use 2 gates for that. There's 4 total on, we have 4 total left, 1 IC chip. Same thing down here, we would need the 32 chip as well. So that's a total of 3 IC chips for this one circuit. This is in comparison to the NAND chip where we have a total of 4 gates and we're using all 4 of them. So inside of our circuit, we only need 1 chip for the entire thing.